Hello everyone, I Vivek Patole from PICT Pune. Welcome you all in this lecture. In this lecture, we are going to study topic from Unit 1, Differential Calculus from Engineering Mathematics 1. Topic is Cauchy's mean value theorem. What are the learning outcomes of this topic? After studying this theorem, students are able to determine the relationship between the derivative of the two functions. They are also able to find the changes between these two functions on finite interval. So let's go for stating this theorem, for which we need to consider the two functions f and g which are defined on the closed interval ab to the set of real numbers. These two functions, they must be continuous on closed interval ab, they must be differentiable on open interval ab, and third condition is the second function g of x, its derivative must not be equal to 0 at any point x belongs to open interval ab. Then there exists at least one point c belongs to open interval ab such that f of b minus f of a divided by g of b minus g of a is equal to f dash of c upon g dash of c. Means what? Ratio of mean rates of increase of these two functions in an interval is equal to the ratio of their actual rates at some point in the given finite interval. So this is the algebraic interpretation of CMVT. Subject to the condition the left hand side denominator is not equal to 0, that is g of a is not equal to g of b. If suppose this g of a is equal to g of b, then what will happen? So g of x will satisfy all the conditions of the Rolle's theorem, and therefore there exists at least one point, say x is equal to c, belongs to open interval ab such that g dash of x becomes 0. So which is contradiction to our third condition of CMVT, and therefore g of a must not be equal to g of b. Right now, to prove this CMVT, we are going to prove this CMVT using Rolle's mean value theorem itself, isn't it? So for which we will define the function phi of x, which is equal to f of x plus a into g of x, and which is defined on the closed interval ab. Now here this a is to be determined and subject to the condition that phi of a is equal to phi of b. Right now, get the phi of a replacing x by a, get phi of b replacing x by b, equate those two expressions, from which we will be getting our a as minus times f of b minus f of a divided by g of b minus g of a. So this is value for a. Now this phi of x being sum of two functions, sum of two continuous and differentiable functions, it is continuous on closed interval ab, differentiable on open interval ab, and already we have considered third condition, which is phi of a equal to phi of b. So all conditions of Rolle's theorem got satisfied. Therefore, there exists at least one point C belongs to open interval AB such that phi dash of C is equal to 0. Now get phi dash of x, which is f dash of x plus a into g dash of x. Replace x by c and phi dash of c by 0. So we will be getting the expression like this. Therefore, f dash of c upon g dash of c, simplifying this expression, it will gives us its value as minus a. Now replace the value of a here, that will gives us f dash of c upon g dash of c is equal to f of b minus f of a divided by g of b minus g of a. So see, this is how we can prove CMVT using RMVT. Already we have mentioned its algebraic interpretation. Again we will note down it. What is its geometrical interpretation? As the CMVT is the extension of LMVT, so its geometrical interpretation is same as that of LMVT, that is tangent to the curve at point f of c comma g of c is parallel to the chord AB. You can easily understand this thing from the below figure. Now there is one note, whatever we have discussed here, this CMVT is the extension of LMVT, but when we replace g of x by x, then this CMVT reduces to LMVT, that is CMVT is the generalization of the LMVT. So this is all about the theory part of CMVT. I hope you have understood this. Now we will go for solving the examples on CMVT. Consider first example. Examine validity of the hypothesis and the conclusion of Cauchy's mean value theorem for the functions f of x is equal to root x, g of x is equal to 1 upon root x on closed interval ab, where this a and b, they are taking positive values only. Solution. Now, as both the functions, they are polynomial functions, ab, they are taking positive values, so they must be continuous on closed interval ab, differentiable on open interval AB because they are taking positive values, and this g dash of x, that is g dash of t, uh, this does not take value 0 for any t belongs to open interval AB, right? Therefore, as all conditions of CMVT got satisfied, so there exists, the CMVT is valid and there exists at least one point C belongs to open interval AB such that f of b minus f of a divided by g of b minus g of a equal to f dash of c divided by g dash of c. Evaluate all these values from the below expressions, then we will be getting it as root b minus root a divided by 1 upon root b minus 1 upon root a equal to 1 upon 2 root c divided by minus 1 upon 2 into c raised to minus 3 by 2. Simplifying this expression, we will be getting value of c equal to root ab, and clearly this root ab belongs to the open interval ab. Hence, the conclusion of the CMVT is examined. Therefore, CMVT is verified. I hope you have got this example. Now let's move on to the second example. If this x lies between 0 and 1, where x can take the value 0, then we have to prove that square root of 1 minus x divided by 1 plus x is strictly less than log of 1 plus x divided by sine inverse x is strictly less than 1. To prove this inequality, now we are going to apply CMVT, for which we can consider this middle term in which numerator as f of x and denominator as g of x, and which are defined on the interval 0 to x, close interval 0 to x. As we know about these two functions that they are continuous and differentiable on the open interval 0 1, close interval 0 open 1. Therefore, these two functions, they are differentiable, continuous on close interval 0x, differentiable on open interval 0 comma x, and also the derivative of this sine inverse x function, that is 1 upon root 1 minus x square, it will not be equal to 0 for any x value or t value in the interval 0 comma x, right? Therefore, all the conditions of CMVT got satisfied, hence it is valid, and there exists at least one point C belongs to open interval 0 comma x such that f of x f dash of c upon g dash of c equal to f of x minus f of 0 divided by g of x minus g of 0. Now get f dash of c from f dash of x, which is 1 upon 1 plus x. Get g dash of c from g dash of x, which is 1 upon root 1 minus x square. So it will be 1 upon 1 plus c divided by 1 upon root 1 minus c square equal to log of 1 plus x minus log 1 is 0 divided by sine inverse of x minus sine inverse of 0 is 0. Simplify the left hand side. Okay, we can write down this expression as square root of 1 minus c square divided by 1 plus c bracket square. Okay, we can take this 1 plus c in the square root as 1 plus c square. Simplifying that expression, we will be getting equality as square root of 1 minus c divided by 1 plus c equal to log of 1 plus x divided by sine inverse of x. I have highlighted this, so please keep in mind this expression because we are going to use it later on. Now, we have chosen the c value from the open interval 0 comma x. So from that, here we can easily write down c is strictly less than x and this x is strictly less than 1, which is the given thing. Now, take the reciprocal of this inequality, we will be getting it as 1 by c strictly greater than 1 upon x strictly greater than 1. Now, apply the componendo and dividendo process to this inequality. We will be getting it as 1 minus c upon 1 plus c is strictly greater than 1 minus x upon 1 plus x strictly greater than 0. 1 minus 1 is 0. Now, we will take the square root on both sides. Therefore, we will be getting square root of 1 minus c upon 1 plus c is strictly greater than square root of 1 minus x upon 1 plus x. Now, if you look at to this left hand side, then c is the positive number which is lying between 0 and 1. So 1 minus c is a positive number strictly less than 1. It is divided by a positive number. So this whole ratio is a positive number strictly less than 1. Hence, the square root is strictly less than 1. Now we will combine these two inequalities and we will be getting the new inequality as square root of 1 minus x divided by 1 plus x is strictly less than square root of 1 minus c divided by 1 plus c strictly less than 1. Now we replace value of this square root from the expression which we have obtained already. So we will be getting the required inequality, which is square root of 1 minus x divided by 1 plus x strictly less than log 1 plus x divided by sine inverse x strictly less than 1. So see, this is how we can apply the Cauchy's mean value theorem to prove such inequalities. I hope you have understood this example. These are the few references. Thanks for watching this video.